So I'd like to present our results on the near-surface iron cation transport in the near-surface region of magnetite, which we've studied by neutron reflectivity and nuclear forward scattering, so precisely by nuclear resonant reflectivity in time spectra. Magnetite is one of the 4 common iron oxides, and on industrial scale, it's used, for example, as a catalyst precursor, most importantly in the Haber-Bosch reaction, as shown here, but also as an active catalyst component in the water gas shift reaction and also in the Fischer-Tropsch synthesis. More recently, magnetite is also being used in the form of magnetite, ligand-coated magnetite nanoparticles as an inorganic organic building block in material science to create hard and at the same time tough materials, which were modeled after natural hierarchical materials like nacre. And as magnetite is ferromagnetic and also conductive, it's also used in spintronics, where it's used as a source for spin polarized currents. And all these applications have in common that they are highly surface sensitive. So we would like to know how surface alterations influence these processes. And surface alterations often also include near-surface cation transport. And we studied this in a simplified model systems because these applications usually take place in rather complex environments. So instead, we used a magnetite single crystalline O1 polished surface, and we studied the process in ultra-high vacuum to get very good control about the environmental conditions. Magnetite is a mixed valence inverse spinel type oxide, and often it has the sum formula Fe3 minus delta O4, so with the non-stoichiometry delta, because the stoichiometry of magnetite strongly depends on the temperature and also on the oxygen potential, and non-stoichiometries in magnetite are very common. And so far, the cation transport in magnetite has been studied mainly for the bulk, but especially with respect to its defect structure because of this non-stoichiometry. And this led to the development of the so-called point effect model of cation diffusion in magnetite. And this model is shown here with a plot diffusion coefficient against inverted temperature for different well-defined oxygen potentials. Diffusion in crystals in general is mediated via defects. And if these crystals are perfectly stoichiometric, these defects result from thermodynamic disorder. And the diffusion coefficient against temperature for stoichiometric magnetite is shown here by the straight line. Becomes more interesting if we add the non-stoichiometry and get a dependence first on the oxygen potential and second on the temperature, leading to this relation between the diffusion coefficient and temperature. So at extremely low oxygen potentials, the main defects in magnetite are interstitials, and a Moose-Bohr spectroscopy study has shown that these interstitials are located in the tetrahedral sublattice. And these tetrahedral interstitials are also mediating cation diffusion under these conditions, as shown here at the bottom. Oh, this was already one step too far. This was octahedral jump. At slightly higher oxygen pressures, the main defects are octahedral vacancies, and they jump, as you might have seen before, within the octahedral sublattice. And at even higher oxygen potentials in this range, magnetite is only metastable. And in this range, we believe that the diffusion is also mediated via the octahedral sublattice via octahedral vacancies. To study the near-surface cation transport, we used a modal system like this. So we've homopatextually grown isotypically labeled iron 57 magnetite thin film on top of a natural magnetite substrate, and then annealed our sample to blur the interface between the thin film and the substrate. And then we studied the interface stepwise after each annealing step to see how the cations intermix. And we've used at first neutron reflectivity, where we get the contrast because iron 57 has a lot or has a much smaller neutron scattering length density compared to natural iron, mostly iron 56. And also side selectivity, selectively by nuclear forward scattering. So in nuclear forward scattering, we use the Mössbauer activity of iron 57 and observe the temporal decay of the excited nuclei via time spectra, which look like this. And as the hyperfine field of tetrahedrally and octahedrally coordinated cations and magnetite are slightly different, this method is also site selective. So we can get distribution profiles for each site in the crystal, and therefore try to observe where the diffusion takes place in the crystalline lattice or in the crystal structure. And if these time spectra are integrated over time and measured over a large angular range, we again get a reflectivity curve, which gives us the depth sensitivity. At first, we needed to study the structure of our sample because, as I mentioned before, the vacancy concentration or the defect structure of the sample is of high importance for the actual diffusion experiment. So we studied the growth of magnetite thin films by in situ X-ray diffraction at the Soleil synchrotron. And here, 3 of the CTRs we've measured after growing a thin film in 8 × 10⁻⁷ millibar oxygen at a low substrate temperature of only 420 Kelvin. And I've shown these CTRs in comparison with a simulation for a bulk truncated magnetite surface and a SCV reconstructed magnetite surface. The subsurface cation vacancy reconstruction is the most common reconstruction on the magnetite 01 surface. And comparing this with the actual data, it's obvious that there are features of both the bulk and the SCV reconstructed surface, which is nice as it shows that we've really grown something which is very, very close to stoichiometric magnetite. And at the same time, it shows that it's not perfectly ordered, most likely due to the low substrate temperature during the growth we used to prevent interdiffusion between the different cations. Probably more important for our experiment is that we got a vacancy or an occupancy profile in the thin film. So we fitted it for the first 3 layers seen from the top. And there is an average occupancy in the thin film of about 0.9 to 0.95. So we have a lot of vacancies in the thin film, which we have to consider when evaluating the diffusion experiments. And the first diffusion experiments we did were with neutron reflectivity. So we went to the Maria beamline at Garching, and there we studied such a thin film. And initially we expected we would get such a nice step profile. But instead we had considerable interdiffusion of the cations already during the growth. And we argued that this interdiffusion during the growth resulted from an oxidative regrowth process, which was observed for the magnetite 01 surface for a lot higher temperatures and higher oxygen potentials. And in this regrowth process, cations migrate from the bulk to the surface of the magnetite when the magnetite crystal is heated under modest oxygen pressures, creating new layers of magnetite on top. And probably during our epitextual growth process, this happened in parallel, leading to an intermixing of the incoming ions from the MBE process and from cations from the bulk. However, annealing our sample only to 470 Kelvin already changed the scattering length density profile, showing that there is interdiffusion starting in under vacuum annealing, at least at 470 Kelvin. And we continued heating stepwise up to 770 Kelvin, and already at 670 Kelvin, we basically had the complete intermixing of the thin film and the substrate cations. So there was a exchange of the cations over a length of about the thin film length of 250 angstrom, already at 770 Kelvin, which is considerably lower than the studies for the bulk have shown so far. So we now know approximately that this diffusion process extends over a quite large length scale. Now we wanted to learn more about its site selectivity. And therefore we used a 70 angstrom thin film, which we studied with nuclear forward scattering. And at first, I'd like to present you the time spectra we recorded in comparison with simulations I made for a perfect iron 57 ratio on the octantet positions. So this ratio should be 2 to 1. And then the time spectrum should look like this. And there are subtle changes in our sample, indicating that the ratio of RN57 on tet and oct positions is not 2 to 1. So that there is already a slight difference of the occupation, maybe resulting from the growth. And this difference further changes during the annealing process. So the cation transport seems to be different on the two sublattices. The reflectivity shows again that the curve or the oscillation is getting smaller and it's moving towards higher angles. So there is interdiffusion, as in the neutron experiment, starting at 470 Kelvin, while the X-ray reflectivity, which is not sensitive to the isotopes, is basically constant, showing that there is more or less no change in the structure. And fitting all these data together gives us site-selective RN57 distribution profiles. And we can clearly see that there is a trend of RN57 to diffuse to the bulk, already starting at 470 Kelvin. And it also shows that most of the change is here in the light blue oxygen octahedral sublattice, while the tetrahedral sublattice shown in yellow basically stays constant. And this is well in line with the Mössbauer results for the bulk, where it was shown that under slightly oxidizing conditions, as we have it here, and we proved via SXRD, the transport is mainly mediated in the octahedral sublattice. In the end, I'd like to present to compare our results with the point-defect model. So the diffusion coefficients we obtained from the neutron and the nuclear forward scattering studies are way higher compared to the stoichiometric case, which makes sense because our sample was not stoichiometric, but they are still lower than expected by the point-defect model for the pressures we were working at, about 10 to the minus 7 millibar. Assuming that most of the pressure we had was water, I also did a simulation for 10 to the minus 12 millibar oxygen, but the diffusion coefficients still would be a lot higher, only assuming unreasonably low diffusion coefficients, oxygen pressures, we would come close to the model. And this is most likely because there was a surface process which slowed down the diffusion. So the diffusion mechanism was not different, but it was slowed down, for example, by a regrowth process, as I described earlier, which was dragging up cations to the surface and therefore slowing down the intermixing of the cations at the interface. So I'd like to come to an end and to quickly summarize. We have seen that we were able to do a well-ordered homotextual growth of magnetite on magnetite with a cation deficit of about 10%. Near-surface cation diffusion was observed to start at 470 Kelvin, mainly on the octahedral magnetite sublattice. And it was considerably slower than bulk diffusion, most likely due to surface effects which decelerated the diffusion along the surface normal or into the bulk. And therefore, surface effects need to be taken into account when treating reactions or processes which might involve near-surface cation diffusion in magnetite. With this, I would like to thank you for your attention and everyone who contributed to these experiments. Thanks a lot.